Okay, so today I'm going to be going over how I got my UART functional on this custom FPGA board. I mentioned in a previous video that my UART on the fixed MIO pins from the processing system was not functional, so I'm going to be using an external FTDI chip to enable this. How it works is I'm going to go through the processing system to the extended MIO pins, and that's going to feed into the programmable logic some of the free IO pins available, and that's going to route to an external FTDI chip. So once we get that functional, we're going to run some of the DDR3 tests that we could have ran with UART functionality, and we'll see how to set that up in Vivado and Vitas here. So let's just get started. So I just want to go into this processing system, go to peripheral IO pins, and rather than clicking one of these UARTs on the fixed MIO pins, you want to go to extended MIO. So EMIO over here for UART 0. You want to select that and hit OK. Make sure your input frequency on your clock is exactly as it's supposed to be. Mine's is 50 megahertz, so I have it as 50 megahertz, so hit OK on that again. And now as you can see, we have this UART functionality exposed on the processing system. So you want to hit this drop down menu, and we want to make UART transmitter and receiver external, so we can have access to them through our programmable logic on some of those free IO pins. So I'm going to click on that, make that external. Click on that, make that external as well. So now we have access to these external ports for UART. So what we want to do is make sure we know what the name of the port is. So we have it as UART 0 RX 0, and same for the transmitter. So you want to go into your constraint file, and you want to assign package pins to these ports. So you want to know what package pins you're assigning to these ports. In my case, if I go into my schematic here, I can see that UART is routed to this 40-pin Raspberry Pi header. I'll show that in a second, but you can see package pins V17 and V18 are routed to GPIO 15 UART, GPIO 14 for the transmitter. So if we go into this 40-pin Raspberry Pi header schematic here, we can see that's routed to these pins here. So how it works is the signal is going from my processing system through the programmable logic of the FPGA all the way to this 40-pin Raspberry Pi header. So we can see in my layout here, that's going to be these two pins over here. So I'm just gonna turn on my camera here for my board, and I can show that really quickly. So you can see I have this wired up over here. So it goes from the processing system through the programmable logic, and it gets exposed to this 40-pin Raspberry Pi header here, which by the way I can use to talk to my Raspberry Pi, whether it be UART or SPI or whatever you want to do. That's available on the EMIO of this Zynq processing system. But you can see this is routed from the process system transmitter to the receiver of this FTDI chip, and same thing for the receiver from the processing system to transmitter of this FTDI chip, right? Okay, so now what we want to do here is just and obviously the ground for the board is connected to the ground of the FTDI chip as well. So let's just go back into the diagram here, and let's just validate our design. And that's good. And what we want to do is run the same usual steps we always do, which is create the HDR wrapper, run synthesis implementation, and generate the bit stream. So I'm just going to do that now. So I'm going to create HDR wrapper. And I'm also going to plug this in. So now that we've generated the HDR wrapper, we can generate the bit stream, and I'm just gonna let that run. Now that that's complete, we just want to export the hardware and boot up Vetus. Okay, let's just let that run. So just go to File, Export, Export Hardware, Next, include bitstream and binary, hit Next. That's fine. Hit Next and finish. So now we're just gonna launch Vetus and carry on from there. So you just want to go to Tools and launch Vetus IDE. Now that we're in Vetus, we want to go to File, New Component, Platform. Let's have this in another folder. Let's just call it UART DDR3 with UART. Select that folder, hit next, and let's select our hardware that we just generated, which is in here, UART. Hit next. Okay, hit next and finish. I'm just gonna let it generate that platform. Okay, platform's been generated, so I'm just gonna build a platform. Just gonna let that run as well. The platform's been generated and built. What we want to do is go to examples here and go to Zynq DRAM test, create new application from component. Names are fine, that's fine. Hit next and select the platform. Hit next and hit next and finish. So it's gonna create this Zynq DRAM test application here, and so I'm just gonna build that. Okay, so now I'm just gonna open up Tera Term. Let's have it on the bottom here. Let's see if we can increase that. Okay, so I'm gonna get my board up here on the side as well. Let's get that going. And what I'm gonna do is just connect. Let's go to setup. Let's get this serial port connection open. So the baud rate is 115/200 for the Zynq processing system, and I know my FTDI chips on COM11, so I'm just gonna hit open now. Okay, so now I can basically just run this program. So run. So there we go. Now we have this DRAM diagnostic test available. So I'm just gonna run through the process very quickly. So I'm gonna test 500 megabytes of length from starting from this address over here. So I'm just gonna let that run and hit 5 for that. So basically we verified our UART functionality already. So now what we're doing is we'll just run some of this DRAM test that we did not run previously, since we did not have the UART functional. So I'm just gonna let this run. This one takes a while to test the full memory length. So we can see no errors here for the full range of the memory test. So what we want to do now is just check the read data I measurement and write data I measurements. So let's just do that quickly. And so this is for read, and we can see that our percentages available, so the I width minimum we've got here is 68%, which is all right. Ideally, you probably want to have above 70%. So this basically tells you, you know, the margin available for your memory controller to sample a bit here, right? So ideally sample at the center, but you know, if you go outside of the center, what's the minimum and maximum time and margin available? So 68% is good as well. 81% is very good, so that's good enough. Let's check. For right now. And we can see similar results. Minimum 71% here, so that's good enough. So yeah, for this test, that's about it. Let's run the memory test we previously ran in my previous video. In that video, I had to use a watch to determine pass or fail, but we can see how convenient it is with UART now. So let's just quickly run that. So I'm gonna reset the processing system here. So let's go to examples, the same memory test from before, create application, hit next, select the platform, hit next again, and hit finish. Okay, so we're just gonna build it. Okay, and yeah, we're just gonna run it with our UART Tera Term available over here. So we'll see how that goes. So you can see here, test in memory region, DDR3, memory controller, DDR. So just gonna give that a moment. So there you go, memory test application complete, successfully ran memory test application. And that's it for the video. So for the next video, as you can see, I've got my UART, I've got my Ethernet cable plugged in here, so verify that that's functional. We'll make a video on that. A lot of fixes to make on that on the Vivado side and Vitas, so just gonna run through that.